So, welcome once again. So, we want to start the discussion on FP hard absolute approximation algorithm. I hope the screen is shared and you can see my screen. So, the example which we take over here, that is about 0 by 1 knapsack problem. Okay. So, you know the problem is the 0, 1 knapsack model as it's an optimization problem. Solvable using dynamic programming. So, optimization problem. Solution, which is given as follows. Vector. This is argument of summation. It's P I. Notations are standard, so I am not mentioning much of them. You know what is Pi, Xi, etc. Equal to 1 to n. Constants subject to summation over Wi Xi is less than equal to m. M is the capacity of the knapsack. This is I equal to 1 to n. Where Pi 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 belongs to I, obviously I plus Xi belongs to, its value is either 0 or 1, so it belongs to 0, 1. Right. I. So less than equal. So this is the problem. That's an optimization problem. Okay. And we have a theorem in this regard. Theorem is approximation algorithm for 0 by 1 knapsack problem. Okay. Forward, not so difficult to understand. So assume there exists absolute approximation algorithm A by 1 knapsack problem Okay, uh, that from the definition of absolute approximation algorithm, we know that exact solution f star I and approximated solution f bar I has to be less than k for some. So I'm not mentioning what are f star I, f bar I. F star I is the exact solution, f bar I is the approximated solution generated by the algorithm A. Okay. So next, let an instance I problem is by okay defined by belongs to 1 and knapsack capacity M. Okay, so and and another instance I dash is defined as plus 1 Wi. Again, I belongs to 1 to n and same knapsack capacity. Only the profits are k plus 1 times the profit in instance I. So we define two instances I and I dash. Okay. And we will show that the algorithm A is generating an optimal solution to the problem instance I dash. Okay. I know that the algorithm A is can generate an optimal solution for the instance I to the problem. So f star I means minus f bar I is less than k. That means A is the algorithm which is producing, generating the feasible solution and hence the optimal solution for the problem instance I. So can that same algorithm A can generate the optimal solution for I dash? So that's we are going to do now. So optimal solution to the problem instances I and I dash are are O is equal to the summation. Optimal solution means are the maximum profits for the time being. I know that it has to be I0, okay, but let's say we find the corresponding maximum profit, thereby we can find out the I0. So our maximum profits P0, the maximum profit for I dash, it is summation over P I, Pi, okay, where X belongs to X section. And summation over to dash. Copy this. Of this profit is K plus 1 times Pi. This is okay. We will see that. So eventually here you can argue that, sir, whether we will have same IO, whether we shall have same WIO. Okay. So we will eventually show that we will have same IO in both problem instances I and I dash. Also same WIO dash IO. Okay. So PO dash is this. So in the next line, what we can show that to plus 1 times summation over plus 1 2. Okay, so this is an important result we have come up to. K dash equal to K plus 1 times the optimal profit to the problem instance I. Okay. Next, what we have in from the definition of absolute approximation algorithm, we say that uh, star I star solution star I. So PO dash is the F star I, PO is the F star I, PO dash is F star I dash, PO is F star I. Where F star I is equal to PO if star okay. So that means what? Okay. So the profits are only differing by a factor of a plus 1. Okay. So if you that means the optimal solution, which is the x0 vector or I0 vector. Okay, this is my mistake. This is x0. That means have same optimal solutions. Okay, as okay. So as 2 is independent of okay of profit, I and I dash will have of uh, they are differing by feasible solutions are corresponding to the profits which are differing by a factor of k plus 1. Okay. Okay, so we done this. Next we do the analysis of that. If bar I dash to uh, approximated solution generated by uh, algorithm A. So if bar I dash is an approximated solution or feasible solution generated by algorithm A. We can write the following. That feasible solution to the problem instance I dash may be an optimal solution, may not be the optimal solution. So if it is an optimal solution, then that will be equal to f star I dash, where f star I dash is the optimal solution to that instance I dash. So if uh, the optimal obtained, if optimal solution is obtained, otherwise it will be equal to, it will not equal to f star I dash. So if it is not equal to f star I dash, then I can say that it is equal to, and let's say f star I dash is the p0 I dash. What is f0 I dash? This is p0 I dash. So what is p0 I dash? Uh, this is k plus 1 times summation over this, right? So it is nothing but summation over, okay, k plus 1 into, let's say profit is pi, okay, where it is I belongs to 1 to what, some L, okay. So okay, because it's a knapsack problem, right? So let's say we are given n number of objects corresponding to n profits, p1 p2 dot 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 pn. So summation over pi xi has to be maximum. So that means all the n objects, all the n profits p1 p2 pn may not be may not be contributing towards this summation. Maybe at least one profit is not, but how this summation is formed, you know. So pi into xi, so xi is either equal to 0 or 1. That means one pi will be either selected or not selected. That is the binary selection, either selected, not selected. No fractional amount of pi will be contributing to this summation result. Okay, so if that means if the optimal solution is obtained, then we can understand the maximum profit will be occurring only if all the profits pi are present in the summation term, and if it is not optimal, then at least one profit term is missing in this summation term, at least one. There may be two profit terms which are missing. There may be three profits which are missing in this summation term. So let's say I equal to 1, so I will be equal to 1 to 1 or 1 to 2 or 1 to 3 or 1 to n minus 1. So that's why we are writing I equal to 1 to L, where L 1 or 2 or 3 dot 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 or n minus 1. Okay, so if optimal solution is not obtained, okay, so this is the model. Okay, so what we have here, so we have f bar I is obviously less than or equal to this summation plus 1 into pi. I equal to 1 to n minus 1, right? And it is, but it is greater than equal to, the minimum value is I equal to 1 to 1, maximum value is I equal to 1 to n minus 1 of this term, if dash I dash, when optimal solution is not optimal. So this is 1 to 1 k plus 1 into pi. That means simply k plus 1 into pi. Plus 1 into pi equal to. So this is, from this we have obtained. Okay, and guys, so we take the right hand inequality f bar I, sorry I dash is less than equal to this. Okay, so we take up that, so f bar I less than or equal to this summation over this. We can say that this is summation over plus 1 into pi minus if this is I equal to 1 to n. Okay, right? So we are adding one term there and subtracting this. So this is equal. Summation 1 to n is your f star I dash. Okay, so from here what we can implies is normalizing the inequality by profit, what you get if bar is less than or equal to star minus. So we are dividing inequality by pi, both side of the inequality. Okay, so this fi dash not my fi is the fi dash is the feasible solution. So feasible solution may be uh, uh, in terms of the maximum profit, or if I normalize it by profit, then it will give us, you know, the 1010 vector. Okay, so so next what we have k plus 1. So next we have the revised model. So let's say this is, you know, solution model. Solution model 4 is modified if 5 to 10 minutes we are coming to end. This is equal to f star I dash star I dash, or this is equal to f, so is less than or equal to less than or equal to r, so f star I dash minus k plus 1. Okay. If optimal solution is obtained, not up. So obtaining the optimal solution is in NP hard that we are investigating. Okay, so this is the model. let's say this is model number 5. So either this will be equal to this or less than equal to this. Now what we take, so as A is, if A is the algorithm is an absolute approximation algorithm, then we must have uh, I less than k, okay, less than equal to k, for example, no issue. Less than equal to k, and so less than equal to k. This we must have if absolute approximation algorithm is A. Okay, so then what is the value of if bar I dash? We have uh, from 5. Okay, from 5, if bar I dash is less than equal to f star I dash minus k plus 1. So rearranging that inequality, we get f star I dash star I dash minus f bar I dash is greater than equal to okay. So the this is not possible. So in inequality 6 and 7, inequality 6 and 7 will be true if only if, okay, the left hand side is 0. Or from 5 you can say that if this, so in model 5 we have f bar I dash either equal to f star I dash or less than equal to this. So if this is less than equal to this, so then this is not satisfying the absolute approximation, it is not satisfying this inequality 6. That means f bar I dash have to be equal to f star I dash. Okay, so in both way we can defend this. So f star I dash has to be equal to f bar. What is f bar I dash? F bar I dash is the feasible solution generated by algorithm A, and f star I dash is the optimal solution to the problem instance I dash. That means the feasible solution. That means here what we can say that thus proved that the absolute approximation algorithm A will can generate generate a feasible solution. Feasible solution. A feasible solution to the problem instance I dash, and that is obviously it will produce a right. So it is arbitrarily producing a feasible solution that comes out to be the optimal solution. Okay. Hence, and generate feasible solution optimal to instance I dash. So can generate a feasible solution that is optimal to the problem stack. Right. Okay. Uh, that it is following the absolute approximation property, which is this. Okay. So therefore we have proved that for therefore 0 by 1 absolute approximation algorithm for say, sorry, 0 by 1 knapsack problem is an NPR. That is the so here we conclude our discussion, and you can ask me if you have any question, or we can stop it.